In this video, we consider yet another example related to the binomial distribution. Suppose that the probability that a passenger will miss a flight is 0.0982. Airlines do not like flights with empty seats, but it is also not desirable to have overbooked flights because passengers must be bumped from the flight. Suppose that an airplane has a seating capacity of 52 passengers. Question A. If 52 tickets are sold, what is the probability that 53 or 54 passengers show up for the flight, thereby resulting in an overbooked flight? Let us unpack this problem. As it stands, in this context, what constitutes a trial? A trial here is a passenger. Will the passenger miss the flight, or will the passenger show up for the flight? So the trial in this context is equivalent to one passenger that can lead to two possible outcomes: either miss the flight or show up for the flight. Show up for the flight. We're going to let our x, the random variable of interest here, be the number of passengers who show up for the flight. So let's write that down. So if x represents the number of passengers who show up for the flight, then in this case, our n, the number of trials, or the number of passenger tickets that are sold in this case, will be equal to 54. And p is the probability that a passenger shows up. The probability that a passenger shows up. If the probability that a passenger misses the flight is 0.0982, then probability of show up will be the complement 1 minus 0.0982, and that will be equal to 0.9018. Then, with that said, we now proceed to finding the probability that 53 or 54 passengers show up for the flight. That will be the probability that x, the number of those who show up for the flight, is either 53 or x is what? 54. This gathers the probability between 53 and 54 inclusive. So we go into StatCrunch and key in the relevant parameters. That is n equals 54 and probability of success 0.9018. Let's do that. Here on my screen, I have keyed in the parameters 54 and 0.9018. So I'm going to click between, and I want between 53 and 54, and I'll hit the compute button. So this gives 0.0259. All right, let's see what is. So I'm going to take that answer back to my working space, 0.0259. Now we proceed to the next question. Suppose that 58 tickets are sold. What is the probability that a passenger will have to be bumped? In this instance, the number of tickets sold, that would be n equals 58 in this case. And then probability of success will be equal to 0.9018, and we're interested in the probability that a passenger will have to be bumped. Probability of being bumped will be the probability that, since the airline has a seating capacity of 52 passengers, an instance of bumping will occur if we have more than 52 passengers. So that will be the realization that x, the number of show up for the flight, is definitely greater than 52. So it could be 52. So that will be it could be greater than 52, which will be 53, or 54, or as much as the number of tickets sold, which is 58. So in this case, this is the probability between 53 and 58 this time, given these parameters. So let's see, let's erase this off. Let's take that off. That cleans up this a little bit. And so that will be equal to, using the same parameters that we had, except what? The n is now 58. So I'll take that to start crunch. I'll adjust this to 58. And I want between 53 and 58. So I'll adjust this to 58 too and compute. So I have 0.4897. With that question completed, we proceed to question C. There is a mini typo here. Let's take the wood out of it. So for a plane with a seating capacity of 270 passengers, what is the largest number of tickets that can be sold to keep the probability of being bumped below 1%? So in this case, we're to assume that we have a plane with a seating capacity of 270 passengers, and we want to know the largest number of tickets. In this case, n is unknown, so that the probability of being bumped is kept to at most below, so less than 1%. Well, the first question we ask is, what parameters are we working with here? We don't know what our n will be to ensure that this condition is met. We do know that the probability of success that we've been using so far is 0.9018. We also know that if the seating capacity is 270 passengers, then a bumped situation, probability of bumped, is probability that number of passengers who showed up will be greater than or equal to 271. So that is, so we want to find the probability of x greater than or equal to 271 being less than 1%. That is the statement of the problem in this case. Statement of the problem. And with that said, it might be time to do a little bit of trial and error for the values of n. So let's pick a number that, of course, is definitely greater than what? 271, because you want the number of tickets that are sold to be greater than this number, which would induce a bumped situation. So let us go into Start Crunch. We have our P set there, and we do want a standard case where you have greater than or equal to, and then 271. So we're going to try numbers greater than 271. For instance, for the values of n, if I try 272 and I compute the probability we have currently on the screen is exceedingly lower than 0.01. That is taking it too far. So I'm going to adjust this. Let me take about, let's say 280. And you see that this is beginning to get a little bit bigger. So remember, the benchmark is 0.01. Remember, we want to keep it lesser than 0.01. So let me keep messing with that. So let me make this 81. Let me see what happens. Still lesser. Let me jump a little bit to 85. This is 0.001. That is reasonably close to this. So I'm still going to continue. Since this is still less than 0.01, I'm going to keep working on this. So let me make this 286. I want to get the first number that will be greater than 0.01. So this is still greater. So let me try 7. I'm going to try 8. And this is 0.012. Take note that when I had 287 here and I computed, This was less than 0.01. But once I changed this to 288, I got a number that is now greater than 0.012. Once I get this number, it tells me that I've already crossed my threshold. I don't want it to be greater than 0.01. So what was the last number I tried for n? It was 287. This is the magic number. So n equals 287. That is the number I want. So the answer to this problem is n equals 287. This is the number or the largest number of tickets that must be sold in order to keep the probability of a passenger being bumped below 1%. With that done, we now proceed to an application of the binomial distribution to check for unusual events. We saw this earlier briefly, but we want to put it formally in words. You see, for a fixed probability of success, as the number of trials n in a binomial experiment increases, the probability distribution of the random variable x becomes a bell-shaped distribution. So the general rule of thumb is that if you find out that n times p times 1 minus p is greater than or equal to 10, you will find out that the probability distribution will be approximately bell-shaped. How is this of interest to us? It helps to serve as the basis for one of the many applications of the binomial distribution to check for unusual events in everyday lives or in everyday random phenomenon. You see, as long as this condition is met, the interval from the mean minus 2 standard deviations plus mean plus the 2 standard deviations gives the non-unusual or the usual observations. Observations outside this interval may be considered unusual. To illustrate, let's see this example. According to CTIA, 41% of all US households are wireless only. In a simple random sample of 300 households, 143 are wireless only. Is this result unusual? In order to check if this result is unusual, we're going to first check this condition to see if it is met by this binomial experiment. In this case, our n is a random sample of 300 households, and our p is the 41%, which is 0.41. So let us check if the answer for n times p, 1 minus p, let's see if it is at least 10. So np, 1 minus p, will be 300, 0.41, 1 minus 0.41, or 300 multiplied by 0.41 multiplied by 0.59. And that will be equal to 72.57, which checks out. It is greater than 10. So since this condition is met, I can construct this interval. So this will go from mean minus 2 standard deviation to mean plus 2 standard deviation. Any number in this range, if it is observed, this is marked off as a usual observation. Any number outside this range, either below mean minus 2 standard deviations or above mean plus 2 standard deviations, is marked unusual. So with that said, let us look at what these values are. So we need to find the mean. Recall that for a binomial distribution, the mean is n times p. That will be 300 multiplied by 0.41, and that will be equal to 123. And the standard deviation is the square root of n times p times 1 minus p. We got the answer for np1 minus p earlier to be 72.57. So this translates to mean that you're finding the square root of 72.57, which is 8.5188. This is the standard deviation there. So with that said, we're ready to find the value of mean minus 2 standard deviation, which is the lower bound here. So that will be 123 minus 2 times 8.5188. And this should give 105.9624. And for the upper bound, that is mean plus 2 standard deviations, that will be 123 plus 2 multiplied by 8.5188, and that gives 140.0376. So any number in the range between 105 and 140.03 will be considered a usual observation. A usual observation. So let's check. What number was observed in this household? Out of a random sample of 300 households, 143 were wireless only. The question we ask is 143, is it in this range? Well, as you might agree with me, 143 is bigger than 140. So 143 is definitely an unusual observation. So the answer to this question, is this result unusual? Is yes, this result is unusual. Is unusual. So with that done, we've come to the end of our discussion on the binomial distribution.